Alright, so in previous videos we've actually talked about matrices, and we've referred to them as a lattice of numbers, of values, and what we might want to do is find the inverse of these matrices. And the whole idea of an inverse is, let's say we have a matrix A. Let me use a different color. Let's say we have a matrix A defined by A, B, C, D. This is a 2 by 2 matrix. Well, we might have the inverse of that matrix, such that when we have A times A, for example, but A times A inverse, well, that is going to be equivalent to 1, 1, 0, 0, like that. And so what we refer to this matrix over here as the identity matrix, And by the way, this applies commutatively as well. We could do the exact same thing as such, where we have A inverse multiplied by A. That is going to be the exact same thing. And so both of these are referred to as the identity matrix. And the identity matrix has many different forms. It can be in 2 by 2 form. It could also be in a 3 by 3 format, 3 by 3 identity. It might look something like this, where we have ones coming across diagonally and zeros surrounding it. And so that is kind of the idea of an identity matrix, where we have very specifically a matrix of a certain order, and it's consisting of all ones on its kind of main diagonal, from the upper left over here to the lower right down here, and zeros kind of in all of the other elements. And so that is kind of the idea behind the identity matrix. And multiplying a matrix and its inverse, if it has one, together creates the identity matrix of a specific order n. And so the idea behind an inverse, like I said, is when you multiply them, you get the identity matrix. Now we also have the idea of what is called a determinant, and so let me bring this to the left over here really quickly. And so the idea behind a determinant is that, let's say again we have a matrix A. Well, its inverse is going to be defined by 1, and let's step back over here. Let's say matrix A is A, B, C, D, and so the inverse of A is going to be defined by 1 over AD minus BC. And there's a significance to that AD minus BC. We'll get to that later. But that is going to be scalar multiplied by the following. It's going to be dA across diagonally, and then we also have negative B, negative C. And so look at what we're doing. We have our matrix, our 2 by 2 matrix over here. This only applies for 2 by 2s. We have a 2 by 2 matrix over here. We take the diagonal values, A and D, we swap them, and we negate the other diagonal values, B and C, and we multiply the whole resulting matrix by a scalar value defined by AD minus BC. And so the determinant of matrix A is going to be equivalent to AD minus BC, and that is for a 2 by 2 matrix. Well, what about for a 3 by 3 matrix? And by the way, I think you can very easily recognize this. What we're doing here is we're taking this value and this value over here, A and D, and we're subtracting it from B and C. That's only in the context of a 2 by 2. So in a 3 by 3, what is this going to look like? Well, let's say we had a different matrix, and I'm going to call that matrix B, for example. Let me write that down. So we have matrix B. Well, that's simply, and we have A, B, C, D, E, F, G, H, I. Well, then we take each of these components, and these are going to be our scalars. And then we have to take the resulting we have to take a minor matrix out from this. And so I'm gonna have to write this down a little better. So we have the determinant, so that's what we're trying to find, the determinant of B. So first we use our first scalar A. And so the minor matrix that we then have to use is EFHI. And so let me show you that minor matrix right now over here. And so we're going to be using this kind of minor matrix over here. And so it's going to be EFHI. And by the way, notice the notation that I'm using here. The notation I'm using here is determinant notation. I'm going to get to that in a second, but it's two straight lines. That is going to be subtracted from what we the second scalar minus b. So the second scalar is b, so we have subtracted from b, and that's going to be the second minor matrix. And the second minor matrix is going to be DFGI. So let me actually write that down like this, because it's going to be kind of complicated to do. But we're going to be ignoring this part. So we have DF and GI over here, and that's going to be our second minor matrix, DF, GI. And then that's going to be added to our third scalar, which is going to be DE and GH. And so you see the pattern that's forming over here. Let me remove this extraneous line over here and over here. And so what we're going to have is DE and GH. DE and GH. All right. So, again, what are we doing here? We have these multiple values in our 3x3 matrix. In order to find its determinant, we take the topmost values, the topmost A, B, and C. We use them as our scalars, and we are going to multiply them by the determinants of the minor matrices. And the determinants of the minor matrices are simply composed of the columns of the second and third rows, and excluding the column that contains the respective scalar. What that means is that, let's say if we're taking scalar A over here, then we're actually going to be using our minor matrices to be E, F, and HI, which does not include the column of A. And then if our scalar is B, then we have the minor matrix DFGI, which does not include the column of B, and the same thing for C. You have to note here, we have that very, very all-important negative over here. This is very important because it's negative, and so we are not adding, we're subtracting a certain value from our total scalars and minor matrices, and that's something that students sometimes forget. And so it's important to remember that we have a negative b a scalar multiplied by a certain minor matrix. All right, so let's look at a sample problem of both 2x2 and 3x3 matrices, finding both the determinants and the inverses. You'll remember earlier, the inverses of these matrices. Alright, so we're asked to find the determinant in the following matrix, and we're given the matrix, and then we're asked to find the inverse of the matrix if it exists. Now, you might be wondering to yourself, shouldn't the inverse of all matrices exist? Well, actually, no. If the determinant of a specific matrix is equivalent to 0, then the matrix does not exist, and you'll see why later on, but as long as the determinant is not equal to 0, then the inverse should exist for that given matrix. But let's first find the determinant of this matrix over here. So we're told that we have a -4 and 9, and we have -7 and -6. So we're going to be multiplying. Multiplying -4 and 9, and then we're going to be multiplying -7 and 6, and then we're going to essentially subtract this -7 and 6 from the -4 and 9, and so we're going to see how that pans out momentarily. So the determinant of A, and we're going to refer to this matrix as A, is going to be equivalent to -4 times 9, -4 times 9 minus -7 times 6. What that results in is -36 plus 42, which is 6. And so that is the determinant of the given matrix. It is not equivalent to 0, And so thus we can continue on trying to find the inverse. What is going to be the inverse? Well, recall that the inverse of a given matrix A inverse, is going to be 1 over the determinant of A. The determinant of A, let me rewrite that much better. The determinant of A multiplied by dA, and then we're going to negate the second diagonal over here like this. All right, so let's do the same thing over here. What we have in order to find the inverse, what we need to do is first we have the determinant, so it's going to be 1 over 6 multiplied by, as a scalar, multiplied by, we have 9 and negative 4. So we have 9 and negative 4. We're going to swap those values diagonally. And then we also have, I believe, negative 7 and 6. We have to negate those values, and so what it becomes is 7 and negative 6. All right, and so now in order to compute this, we're just going to be doing scalar multiplication on this matrix that we have over here. And so what that results in is 9 over 6, which is equivalent to 3 over 2. 7 over 6, which is just going to be equivalent to 7 over 6. Let me write that down. Next we have negative 1, because negative 6 over 6 is negative 1. And let me write that better. And then we have negative 4 over 6, which is just negative 2 over 3. And so that is the inverse of the original matrix, negative 4, 9, negative 7, 6. Let's actually prove that this is the inverse, and we can actually do that as such. We can check, let's write this down, we can check whether our work is actually accurate. In order to do that, let's first write the notation, the necessary notation. So we have A times the inverse, and so we're told that we'll call that negative 4, 9. We also have negative 7 and 6, and we're multiplying that by 3 over 2, negative 1, 7 over 6, and negative 2 over 3. All right, excuse the bad handwriting. And so in order to actually find or ensure that this is a proper inverse, what we need to do is ensure that the resulting multiplication comes out to be the identity matrix. Okay, so what we first need to do is multiply the negative 4 by the 3 over 2. What that results in is negative 12 over 2, which is negative 6. Add that to negative 7 times negative 1, which is plus 7. All right, so that's the first value over there. The second value is negative 4 times 7 over 6, which is going to be negative 28 over 6. And then we also have negative 7 times negative 2 over 3, which is going to be 14 over 3. So we're adding that over. Actually, we can simplify that or change that a little bit to be 28 over 6 as well. So 28 over 6, because 14 over 3 multiply both the numerator and denominator by 2, it becomes 28 over 6. All right, now we move on to the second row. 6 times 3 over 2 is going to be 9. Add that to 9 times negative 1. Well, that's just negative 9. And then finally, we have 6 times 7 over 6, which is just 7. Add that to 9 times negative 2 over 3. Well, that's just negative 6. All right, we're seeing this pan out in front of us. We have negative 6 times plus 7. That's 1. And 7 minus 6 is also 1. Negative 20 over 6 added to itself is just going to be 0. And 9 minus 9 is 0. And so that is our identity matrix. And thus, we have done the question correctly. All right, we're going to move on to an example of a 3 by 3 matrix and its determinant and its inverse. All right, we're asked to find the determinant of the following matrix, then find the inverse of the matrix if it exists. Well, let's first find the determinant. Now, we first need to identify our scalars, if you'll recall. We have to identify our scalars, which are going to be, in this case, negative 1, 3, and 2. All right, so let's get the hang of that. So we have the determinant of A. Whoops, I keep on writing it like that. Determinant of A, which is going to be equivalent to negative 1 times the determinant of, Now we need to identify our minor matrices. So excluding this column, which is -1, what we're going to have is -5 times 6, -5 and 6, and -3 and 2. So -5, 6 over here, 2 and -3. Subtracted from our second scalar, which is -3. And then our minor matrix is going to be composed of 3, 4, -3, and 6, because we're excluding the column containing 3. Finally, we're adding that to 2 times the determinant of the third minor matrix, which is 3, -5, 4, 2. All right, so we have the respective, we have the expression that we need to compute, essentially. And so now let's actually, find the determinant of the given matrix. So first off, we have a scalar -1. We're going to multiply that with -5 times 6, -5 times 6, subtracted by -3 times 2. All right, second value that we have over here is going to be 3 times 6, 3 times 6, subtracted from -3 times 4. And finally, the third value, and let me just move on over the screen. The third value is going to be 2 times 3 times 2, minus 4 times -5. Again, we're taking the diagonals, subtracting them by the second diagonals that we have over here. And so that's how we're getting all of these determinant values for the minor matrices. Let's compute this really quickly. So we have -1 times -30 plus 6. So -30 plus 6, last time I checked, is going to be -24. All right. The second determinant is going to be 18 plus 12, which is 30. And finally, the third determinant that we have is going to be, I made a small error, a very small error. This should be 3 instead of 2, but hopefully it shouldn't impact the problem that we currently have. Let me change that as well. And finally, the third determinant that we have is 2 times the determinant, which is 6 plus 20. 6 plus 20, which is 26, actually. I can just write that down. All right, so we have 24 minus 90 plus 52. So 24, and then all of that is subtracted from 90. 52 plus 24, last time I checked, that's going to look something like 76. 76 minus 90 is going to be -14. And so thus, that is the determinant of our matrix. But now we have to find the inverse. And we know that an inverse exists because, the value of the determinant is not equivalent to 0. And so what is the inverse going to be? Well, unfortunately, we can't actually go into the inverse of 3x3 matrices today because that involves cofactors, and that is beyond the scope of a normal pre-calc course. But normally you would find the inverses using a calculator. I'm going to show you how to actually do that on a normal TI-84, which is a graphing calculator used in pre-calc courses. So let's move on over to an online TI-84. Alright, so in front of us we have a TI-84 plus CE. Now, these instructions might be different for different calculators, but for TI-84s, which are generally used in pre-calc classes, these are the general instructions for finding an inverse of a 3x3 matrix. So let's first go on clear this. And so the first thing we're going to do is click on that alpha button over there. We're going to click on zoom. Now the pop-up is asking for us for the number of rows and columns in our matrix. So I'm going to click on the up button a couple of times, and we're going to click on enter to enter the 3 rows and 3 columns. So going on back down, we're going to click on OK. And so now we have a blank matrix in front of us, and now we can actually input our values. So we have -1, we have 3, we have 2, and then over here on the second row we have 3, -5, and -3. And then finally, for the third row, we have 4, 2, and 6. So we have 4, 2, and 6. Now to find the inverse, we just have to bring the power of this matrix to -1. And so we have the power button over here, and we bring it to the -1 power. And so now we just click enter, and we're given the matrix, the resulting inverse matrix right in front of us. And so actually, if you compare these values to the actual values, in that first row and first column over here, we're supposed to have 12 over 7, and I believe this value should be equivalent to 12 over 7. Yes, it is, 1.714, 1.714. This middle value should be 1 over here. Over here we have negative 1 over 14. And so that is kind of the instructions for finding the inverse of a 3 by 3 matrix. I'll be posting the PDF of the whiteboard that we had on earlier. I'll also be posting the instructions for finding the inverse of a 3 by 3. Thank you for watching this video. Hopefully you enjoyed it. If you had any questions, please feel free to leave them in the comments and I'll try to get to them. Otherwise, thank you so much for watching, and yeah.